All right, so with the combination of Lewis structures and Vesper, we can take the shape of the molecule and its polarity, right? Is the molecule polar or nonpolar? So for example, something like HF, right? Fluorine is more electronegative than hydrogen, and so it has a partial positive area and a partial negative atom. So it is indeed polar, right? And being able to determine whether molecules are polar or nonpolar is going to be important for our next section. So the first requirement of something being polar is to have a polar bond. However, that is not enough for something to be polar. So for example, if you had a dipole going like this, and then another dipole going into it, right? If you think about what this is called, it's called vector addition. But really, if you think about these two things, they would actually cancel each other out. And so there would actually be no net dipole here. And so this molecule would actually be nonpolar because these dipoles are opposing one another. Same thing for a scenario when they're facing away. This is still nonpolar, right? They are opposing one another. Or, you know, up, down, this kind of thing, still nonpolar because they are opposing one another. In order to be polar, the dipole arrows must sum together. They must be facing the same direction or approximately the same direction. So if you had a scenario that where they're both kind of pointed upwards, if you think about how these would sum, it'd be a straight arrow up, and so this would indeed be polar. And so let's take a look at some of our molecules here. In this first one, CO2, right? Oxygen is more electronegative than the carbon. So the dipole arrow is going to go like this. So you might think, oh, it's got a polar bond. It must be polar. But if you think about the shape of this, these dipoles actually cancel out. And so this is non-polar. What about here? Well, boron is actually less electronegative than hydrogen. It's a little funky one. But same thing here, right? We have our dipoles, and you can see they're facing all opposite directions. They're all facing opposite directions, so they're going to cancel out, and we're going to have a non-polar molecule overall. What about over here? Hydrogen is less electronegative, so we have one going like this, one going like this, one going like this, and then we also have this negative charge up here from the lone pairs, right? So you can see they're all combining together, right? So up on top of the molecule, we have a negative charge, and down towards the hydrogens, we have a positive charge. So this is indeed polar, right? And so one thing you can look up if you're confused about this stuff is electrostatic, right? So we can Google NH3 electrostatic potential. And then go to images. And so you can see a whole bunch of different images, right? You can see this one's pretty good. I like this one. You can see the nitrogen on top right here has a negative charge, while the hydrogens have a more positive charge. So you have a net dipole. Yeah, this one's a pretty good one. Pretty good example here. You can see N2 does not have a dipole, right? Cl2 doesn't really have a dipole. NH3 does have a dipole. So take a look at these things. Think about polarities. Think about vector addition. Be comfortable with this material because it's going to lead into the properties of solids and liquids, which is what we'll be going over next.